Hey, advanced chem students, this will be the last day of notes going through going from petroleum products or uses of hydrocarbons through polymers, which we'll talk about at the end after we talk about functional groups. So let's go ahead and get this started. So there we go. I'm not going to be able to write everything on here, but I'm going to do the best I can. So the first thing we're going to talk about are going to be kind of where the hydrocarbons come from. So hydrocarbons come actually from organisms that were here millions of years ago, fossils or fossilized and decayed plants and animals from quite a long time ago. Let's see, someone has changed my color. Let's change that back. That's silly. There we go. Actually, let's do some blue. Here we go. Do some blue. So let's see if that worked. Yeah, it did. Yeah, from fossils from millions of years ago, the decay of organisms actually gives rise to fossil fuels. Now, fossil fuels kind of incorporate everything that we get from, and we call it just petroleum. Petroleum products include, gasoline, oils, asphalt, all different lubricants and things. Some solvents, and we'll talk about a little bit of those and kind of how we get to them. But basically, if you pump oil out of the ground, it's just raw petroleum products, just hydrocarbons, millions and millions of different hydrocarbons. Those things need to be separated. The way they're separated is by a process called cracking or fractional distillation. So what you do, or what you don't do, but what people do is they this is done in a refinery. And so what you do is you heat up the sludge, the basic petroleum product that you have once it's filtered out, and you separate it by boiling point. So you heat it up in a stack, and I'll show you a picture in a second, but you heat it up in a stack. And if the stack is like this, each area along here will be, so down here is the heat source. The farther it is from the heat source, the colder it is. And so what happens is they'll condense at different temperatures, become liquids, and then be captured, and then go to another stack to be further separated by boiling point. So the first separation may be by hundreds of degrees C, the second one by tens of degrees C, the next one by single digits of degrees C, so that you refine it until it is in, till you have appropriate compounds or specific compounds. A great example is gasoline. So gasoline, the more pure the gasoline, the better it burns, is based on its octane percentage. And so gasoline essentially is lots of different compounds, but the more octane that you have, the better it burns, the more pure that gasoline is. And so you'll pay additional monies, or you'll pay more for gasoline that has a higher content of octane. So that would be an 8 carbon compound, or close to a mix of compounds that are around 8 carbons long. But like in your barbecue pit at your house, if you have a barbecue pit, it uses propane gas. And so that's a 3 carbon compound. And so the majority of those in there, and almost all of them, are just straight propane. The propane is liquefied at high pressure, but when it's opened up to the atmosphere, it comes out as a gas. And so you can have a large amount of it in, say, your little 5-gallon tank. It might last several weeks or months, and I guess on how often you use it. But when it comes out as a gas, you can light it and burn it safely. There are other ones too that you're maybe familiar with. Lighters, for like barbecue pit lighters or cigarette lighters, those use butane, and the butane is in liquid form when you're looking at it inside the lighter. But as it exits and goes in the atmosphere at a lower pressure, it turns to a gas, and so then it ignites. Anyway. So we're actually very fortunate in the United States to have a great deal of this natural gas, just kind of showing you what the components there of natural gas. The majority of natural gas is methane, highly flammable, excellent fuel. We are fortunate to have a great deal of natural gas in the United States. Although cost effectiveness, it's easier to get a lot of these products from other countries than it is to actually capture ourselves. But we're working on that. Or we're not working on that. We'll see how it goes. So here's an example of fractional distillation or cracking. What you're doing is separating those hydrocarbons so that they can be used in more useful molecules, or in certain so that they're refined into just single categories like propane or butane or octane or so forth. Now, as far as coal is concerned, coal is actually a solid product from decayed plants. Coal is an excellent fuel source as well, but it does contain quite a bit of sulfur, kind of depending on which coal it is, but it contains a great deal of sulfur, and that sulfur goes in the environment and the atmosphere, and it can produce sulfuric acid, which produces acid rain, which is a whole nother topic of discussion. But these are just talking about where these carbon compounds come. These are the primary sources of the hydrocarbon compounds. This is showing you some of them. Now, this is a very simple refining process. There would be hundreds of these stacks that they would go through. So if you were to drive down to Galveston and look out over Texas City, you would see thousands of stacks, some of them on fire actually at the top, as they burn off some of the leftover gases, the methane and things that we're not collecting, or just burned off. The things that are collected, and you can look on here, there's gasoline kind of way up here at the top. That would be a smaller hydrocarbon. Aircraft fuel in here a little bit lower. If you come down, where is diesel fuel? I thought I saw it on here. Maybe it's, oh, there it is. There's diesel fuel. So here's diesel fuel in here. And so these are distillates, or things that come as a part of actually distilling, trying to get gasoline or other fuels. That actually has a great deal to do with the cost of these. If the refineries are running, then the diesel fuel and the distillates will actually be a little bit lower. If they're not running as much and producing as much as they normally do, there becomes a larger demand for them, and the prices go up. We're seeing a lot of that right now, actually. And then down here at the bottom, you see things that are solids, basically at room temperature, like asphalt, or you have greases down here, lubricants and such. So the last thing that we need to talk about in this, well, almost the last thing we have to talk about in this group, or in this unit, is functional groups. And so functional groups are different things that could be attached to carbon chains. Now, we're just scratching the surface here. There's lots of functional groups. These are primarily the ones that you'll see in second year and first and second year chemistry in college. But you have a long carbon chain, and no matter how long that carbon chain is, rather than tell you how many carbons it is in total, what we'll do is we'll just use, so to say any random carbon chain, we'll use the letter R. So when you see R bonded to something, it means a long carbon chain of whatever length, could be 2, 4, could be 100, doesn't matter, bonded to whatever that group is. And in this first group, it's going to be hydrohalic carbons or halohydrocarbons. Halohydrocarbons are going to have halogens attached to them. Alcohols, a hydroxyl group, ethers, aldehydes, ketones, carboxylic acids will all have double bond oxygens with maybe an alcohol group as well. And then esters are kind of a mix of carboxylic acids and alcohols. And then we'll finally talk about amines. We'll go through each one of these steps. They're going to kind of pop up on the computer. So if you need to pause and write some of these things down while I'm talking, or in the midst of my talking, if I talk too much, just pause and go write them down. But yeah, so and these kind of fly in on the PowerPoint screen, but on my little PDF thing here, they're just going to show up. But you can fill these out while I talk. So halocarbons are going to be things that have that R group, or that hydrocarbon chain, bonded to some halogen. That halogen might be a chlorine, it might be a bromine, a fluorine, whatever. And we've already done some of these when we were talking about naming compounds before. So you would have your backbone chain, say it was like down here on the bottom, 1-chloropropane. You would just say propane. If the chlorine is on the first one, you don't even have to say the understood number 1. You could just say chloropropane and you would know it's on the first one. One thing that is missing from these diagrams here is you really should be putting the lone pairs of electrons around the halogens. Typically, a lot of these Google images we pull don't have them. The AP test would want you to see them on, that they need to be on there. So make sure you're drawing your lone pair electrons. Up here at the top, the very first one that you wrote in, I think, is chloromethane. Methane, meth being the prefix for one carbon compound. And then of course the halogen bonded to it is a chlorine group. So it'd be chloromethane. The second one here, these are carbons with the appropriate number of hydrogens in shorthand notation. I would prefer you guys not write it in shorthand notation, but it's okay. Please don't do that on your exams for us. Write it all out, unless of course it's benzene, like down on the bottom. But this one here would be, let's see, we've got what, we've got 1, 2, 3, 4 carbons. So that would be butane. I've got 2 iodo groups, so that's diiodobutane. And you would have to say which carbons they're on. They're on, of course, the second and third carbon. I need to go ahead and write these dots in here as well. They're missing from all of these. And then the last one, I kind of skipped around a little bit. Bromobenzene. Benzene is the longest carbon chain here. It is possible to have it written as a phenyl group, but this isn't a carbon chain here, so we wouldn't call this like phenylbenzene or phenylbromine, excuse me. We'd actually call it bromobenzene. Just like if you had benzene with, say, a methyl group on it, there's your benzene and a methyl group off to the side, or on one of those, you would call that methylbenzene, not phenylmethane. The longer carbon chain here is actually the benzene group or the benzene ring. So some of the things that it makes up, whether you're aware of it or not, are CFCs or chlorofluorocarbons. These are used in refrigerants. Chlorofluorocarbons kind of were outlawed in the 80s, the 1980s. Not entirely. There was a huge push to save the ozone layer. I was alive for that and listened to it all, and I jumped up and down and screamed about the ozone layer as well. It has actually, as I understand it, recovered a little bit. CFCs were actually banned from use in aerosol cans in the United States and most of the world. So we don't use them in aerosol cans anymore, but they are still used in refrigerants. There are a couple of different ones in particular that we use here. They are R22 and 410A as far as freons that we use in our air conditioning units. They're also used in RVs and cars and other things, but primarily outside of the refrigerants, they've been kind of outlawed. Okay, so sorry about that. I had to go do something, but anyway, so CFCs are pretty much banned from aerosol cans, except for, I think the only use of them are refrigerants now. But anyway, I could be wrong. Alcohols. So alcohols will have a hydroxyl group attached to it, which is an OH group. So you see that OH attached to an R over there. That's an alcohol. Now, they can be any different length of carbon chain, and the alcohol does not have to be on the end of it, right? Just like the halocarbons or hydrocarbons, if you had a halogen on there, it could be on any one of them. The same thing is true of alcohols. And depending on where they're located, they kind of give rise to different behavior, I guess I could say. But here, so what we've got in this one right here, this first one, 3 carbons long, that's propane. What you do is you delete the E and then you add OL as an ending. So that would be propan, you delete the E and then have OL as the ending. Pretty easy to name. You just have to add OL to the end, deleting the E. So if it were octane, it would be octanol. If that alcohol was on the second or third carbon, you would say like 3-octanol. And then on the third carbon would actually be that alcohol group, that hydroxyl group. If you look over here on this second one here, we've got propane triol or propantriol. This one, you have 3 alcohol groups. They're on the first, second, and third carbon. If this were something that we asked you to do, which I don't think we really would, you would have to say that there are 3 of them, and you'd have to say where they are. And that's why it says TRI, the tri meaning 3 over here, and then OL. You could have a diol as well. You could have a tetraol as well, but that's not really what we're after. We just want to show you some of the ones that you would see in real life. And that one right there has a hydrogen underneath that arrow I can't delete. But this one right here is actually glycerin or glycerol. It is used to treat burns. It's kind of a soft, sugary, almost substance, but you can buy it over the counter. If you wanted to, because of all those extra hydroxyl groups, it increases the hydrogen bonding in water. So you could actually add it to the bubble solution. And instead of making little tiny bubbles, you make really large bubbles. I've done this in the past, about 4 or 5 milliliters to a half gallon of bubble solution will make some really awesome bubbles. So naming some simple ones, and this is kind of what we'd like you to do, is right here, we've got 1, 2, 3 carbons. So that'd be this is the same one as before. So propane, take off the E, propanol. You could say 1-propanol if you wanted to, or N-propanol. You don't need to do that. Since it's on the first carbon, it's just propanol. Ethanol right there, that's drinking alcohol. That's just 2 carbons. And we'll go through and I'll talk a little bit about these. I'm not interested really that you guys know all the stuff about them, but just as an aside, alcohols do exhibit hydrogen bonding, so they're mostly going to be soluble in water. The larger that they get, however, more of those nonpolar groups are actually going to be hydrophobic. And so their ability to dissolve in water will actually decrease with the number of groups they're added to. If you look down here on the bottom, we've got a series of alcohols drawn here for you. And the first one, methanol, that's super soluble in water, used mainly as a cleaning agent, but it's called wood alcohol. Ethanol is your drinking alcohol, the second one there. The third one here you might recognize. This one is 2-propanol. It's also called isopropyl alcohol. This would be what you have in your cabinets, cut or abrasion, you clean it up, or you want to sterilize something, you would use isopropyl alcohol. The one on the far right, tert-butyl alcohol, has a little bit of properties of both polar and nonpolar substances, with it having a tertiary alcohol, or 3 carbons bonded to the carbon that's bonded to that alcohol group. They can be called as primary, secondary, or tertiary. What they're referring to is that carbon that's there, how many things is it bonded to? If the carbon that is bonded to it is bonded to 2, it's called a secondary alcohol. If the carbon that is bonded to the hydroxyl group is bonded to 3, it'd be called tertiary. Oh, I didn't talk about denatured. Look at that. So denatured alcohol, this is what we have in the lab for you guys. You can buy this at Lowe's over the counter. But the difference between denatured alcohol and drinking alcohol is essentially a toxin that's added to it so that it makes you sick. So they can sell it for super cheap. You can just pay a few dollars to get a gallon of alcohol, of denatured alcohol at the store. But if you went to a liquor store and tried to buy a gallon of alcohol, it's going to cost you quite a bit of money. The stuff that we use here in the lab is also 95% denatured alcohol. So you guys are not messing around with alcohol that's drinkable. We would not do that to you. And here's just some more information about the same stuff that I was talking about. Ethanol's up there on the top right-hand corner. Isopropyl alcohol down here on the bottom right. A couple other alcohols, phenol, you may recognize antifreeze as well. Ethylene glycol is used in your radiator, your cooling system of your car, and or boats. Even, well, actually, no, boats pump it from the water. Interesting. I have to think about that. There may be some applications in boating industry as well. But anyway, it is used in your car as an antifreeze, but it's also an anti-boil. Not quite as much. It doesn't change the boiling point as much as it changes the freezing point. It effectively changes the freezing point a little more than 3 times the amount it changes the boiling point. But what it does is if you were to graph, say, you know, the freezing point of water and the boiling point of water, as we've done before, what it does is it moves this up. So it goes above 100 degrees and it moves the freezing point down so that it goes below 0 degrees C. The effect on the freezing point is greater. What it does is, because it has 2 hydroxyl groups there, it actually increases the hydrogen bonding in the water and keeps it in the liquid state for a larger temperature span. So maybe -14 all the way to maybe 105, 106 degrees or so, if you add this per gallon. And I forget, I think it's a 50-50 ratio that it's added in your as antifreeze in your car, but I don't remember. It's been a little while since I've done that. But anyway, excellent. It's something certainly necessary if you're in a climate where your car is going to freeze, or it's going to go below freezing where your car is parked. That's certainly true up north, and as in Texas, it's been that way for the last couple of years for sure. So moving on to our second, or I guess this is the third functional group, if we include halogens, are ethers. I kind of like ethers because they're really easy to name. Ethers, you've got carbon compounds on one side and the other side of an oxygen. So I say you've got carbon compounds on ether side of the oxygen. So these are ethers. So they're named alphabetically. So you have the oxygen in the center, and I see a methyl group on the right and an ethyl group on the left. So this is the methyl group, this is the ethyl group. So it would be named ethyl first in the alphabet, methyl second, ethyl, methyl, ether. If I look at the one to the right of it, I've got this benzene group over here, which when it's attached to a carbon chain is called a phenyl group. It would be, and I've got another 2 carbon member over here. This would be ethyl phenyl ether. Now, you may have heard of diethyl ether. Diethyl ether was used as an anesthetic early on, so it actually puts people out. And there we have Curious George sniffing the ether, but whatever. Okay, yeah, that's ethyl ether or diethyl ether. The next functional group is aldehydes. Aldehydes are a carboxyl group. So there is a carbon double bonded to an oxygen here on this, what we call carbonyl carbon. And so it forms this group here. This group is actually used in oh goodness, 4 different functional groups. The first one being aldehydes. Aldehyde must be on the very end of the compound or end of the carbon chain. Now, in the case of this first one, methanol, you only have 1 carbon, and so it's just meth. What you do is you take an E off, just like we did with the alcohols, and you add Al instead of Ol. So it'd be methane, but methanol, excuse me. Methanol, Ol would be an alcohol group. With an aldehyde, you just add Al. So this one would be 1, 2, 3, 4, 5 carbons. You include the one with the oxygen bonded to it. 5 carbons would be pentanal, but I also had this methyl group on there. If an aldehyde is present, and usually that's true for any functional group that is at the very end, you start counting at that functional group, regardless if the methane had been over here. If the CH3 had been over here, the methyl group, you would call it 4. You wouldn't go closest to the methyl group like we have in the past. You would start at the functional group. So it kind of dictates numbering a lot like a double or a triple bond would. And methanol is also called formaldehyde. Form means 1 or 1 carbon, just like meth does. It's just a little bit different. It's an older name. But formaldehyde is used as a preservative. And those of you that took biology know what formaldehyde smells like when you guys did either frogs or pigs or cats in your dissections. Those were soaked in formaldehyde. There's some other ones that are aldehyde, common ones. Cinnamaldehyde and cinnamon has an aromatic ring, which gives it smell, and it has a little odor also from the aldehyde there on the end. Acetaldehyde, it's used as a chemical. It actually causes hangovers. And over here, we've got butanol, smells like your sweaty feet. These aren't things you guys need to know. I just want to tell you that they're kind of out there and that they exist. Another one of using these carboxyl groups, or that has carboxyl group in it, is a ketone. So a ketone doesn't have it on the very end, it has it in the middle. And so if this, if this were actually, the way I always remember it is that this is like kind of like a key, right? And so these are the points on the key. They're in the middle. They're not at the very end. So ketones are always going to have that C double bond O in the middle of the compound. Not exactly in the middle, but not at the beginning, I should say. So if we look at that first one, the way you name them is very similar to the other two. You say propane because there's 1, 2, 3 carbons. Take off the E and you add ONE for ketones. So that would be propanone. Because they're going to be in the center of these, this could be called 2-propanone. But since that's the only place it could be to be a ketone, it's okay to just call it propanone. But on heptanone, there's several places it could be. It could be on the second all the way through the 6th carbon. So you actually have to say what number carbon it's on. And in this case, it's on the 2nd carbon. So we say 2-heptanone. And then there's a couple others down here on the bottom done the same way. This pentanone is bent just so in case you guys see it. Remember that these carbons will spin on their axis, these tetrahedral groups. So they're not really straight chains, not exactly straight in 2 dimension the way we always draw them. They're really a lot more like this at different angles to each other, 109.5 degree bond angles to be exact. So you got 3-hexanone there as the next to last one, and then of course 2-pentanone. An example of a ketone is propanone, which is actually called acetone, is its common name. And acetone is used as a nonpolar solvent. It's used to remove fingernail polish, for instance. You can also use ethanol, although acetone works way better. So carboxylic acids, here's another one of the functional groups. We're kind of getting towards the more complex ones. The carboxylic acids will have a carboxyl group, that's C double bond O, but they also have an alcohol group attached to them. They have both. And because of that, this oxygen as well as this oxygen, it makes the bond to the hydrogen very weak. And so it dissociates the hydrogen. It becomes an acidic hydrogen. They're weak acids, but they are acids nonetheless. And so that's why they're called carboxylic acids. To name them, you do the same as we've done before. You drop the E and then you add oic acid to the end of it. So if it were 2 carbons, that's ethane, you would take off the E and do ethanoic acid. Same thing with something that had 4 carbons, butanoic acid. There are some common names attached to these on this PowerPoint, but you don't really need to know those. If it were just a single carbon, it'd be methanoic acid. And of course, if there were 3 carbons, that would be propanoic acid. So esters, getting close to the end here. Esters are actually a combination of an alcohol and a carboxylic acid. So in dehydration synthesis, a water molecule is removed and an alcohol will bond on this end with a carboxylic acid on the other end. They're named with the one that has both oxygens on it. So if this one right here has both oxygens attached to that carbon, that ending will get the O8 ending, and this one will get a YL ending that's only bonded to 1 carbon. So this would be called, that's just 1 carbon over here on the right, methyl, and then the other one is 2 carbons, F, you take off the E and you add O8. So it'll be called methyl ethanoate. Looking at this one here, a single carbon, they both be named the same way. That would just be methyl methanoate. Oh, my goodness, look at that. So almost finished here. Esters, like I said, are the combination of 2. So you have an alcohol and you have the carboxylic acid. So you have the alcohol here and the carboxylic acid here. So a hydroxyl group and a hydrogen are going to be removed in water, and then you end up with the ester. Again, it's dehydration synthesis or dehydration reaction, if you like, or condensation synthesis is another way to say it. But you pull the water out and you actually can bond the 2 together. And esters show up in lots of different things, especially odors. You've got apple scent here as an example, smell of rum and other things, raspberries, whatever. But yeah, they do have certain odors to them. And we used to do a Stinky's lab where we actually made some of these, and then you identify what the smell is from what you sniff or smell. But we don't do that anymore. The last functional group are going to be amines. Amines are going to have an NH2 group on them. So some carbon chain with NH2. This one's weird though, because amine groups or amino groups can actually be with another functional group. Now that's true of everything, and you would end up having common names, but this happens so often that we actually have specific ways to name them. So very simply put, if you have just the amine and that's the only thing that's bonded to it, you would call this 1, 2 carbons F, you call it ethylamine. You just say ethylamine. But if it's an amino group, in other words, you've got some other suffix representing another functional group, you use amino as a prefix to say that there's an amine group and whatever the other suffix is. That could be an alcohol, that could be a carboxylic acid. It wouldn't be an ester or an ether, but it could be an aldehyde. And so if those things are present, those would get the suffix ending and amino would be at the front. So this one here is just cyclohexane. It'd be better if we didn't have this one looking like benzene. Had this been a benzene ring, it would be called phenylamine, but that's okay. On the bottom here, we have one where we have a carboxylic acid and an amine group. You would actually name the propanoic acid as the ending there, and then you would put amino in the front. Because that is going to dictate what the numbering is, that first functional group, the amine group, you'd have to be told what number carbon the amino group is. It doesn't necessarily have to be on the end. It could be in the middle or whatever. So you kind of be careful there. But yeah, so amines are weird because most of them are just going to be YL amine, so butylamine or methylamine or ethylamine. But if they're in there with more than one functional group, the other functional group is going to take precedent because it's a suffix, an ending of the word. And amino is used as the prefix in those cases. So this is some examples. This one is not in your notes, but if you had to go identify them, I wish you couldn't see it. I wish I could cover it up, but I can't. But right there is an example of a ketone. Notice that it's in the center of those 4. So that would be butanone. 2-butanone to be specific. You would need to say where that is. For carboxylic acid here, notice I've got 1, 2, 3, 4 again. So this one would be a carboxylic acid. It's got C double bond O with that alcohol, that OH group on it as well. That's a carboxylic acid. 4 carbons, so butanoic acid. This one here is an aldehyde. Notice that you've got the carbonyl carbon bonded to that oxygen at the very end. That's an aldehyde. Had it been in the middle of it, it would have been a ketone. This is 6 carbons, so it's called hexanal. And then this one right here, there's 2 more, I think, after this. That's an amine. That would be propyl, 1, 2, 3 carbons, propylamine. There's nothing else added to it, so it would be the suffix for the amine naming. And then here, this is an ester. It's got that 2 oxygens on 1, 2, 3, 4 carbons. So that would be the butanoate. The other one has 2 carbons, so it would be ethyl butanoate. And then the last one actually has 2 different functional groups on it. And it's got a substituent. It's got a methyl group on it. It's got a hydroxyl group on it, an alcohol group. And it's also got a halogen. So this one would be named as a bromo group, an OL ending of alcohol, and also a methyl group on whichever carbon was appropriate. And I think it's the second. I think it would be named 1, 2, 3, 4, 5, 6 here. So this would be 5 bromo, 2 methyl, 1, 2, 3 hexan OL all. So, oh, there it's right there. 5 bromo, 2 methyl, 3 hexanol. Yeah, right there. So the last thing to discuss before we finish up here are polymers. Polymer is actually a larger molecule that's formed by the repeating addition of individual molecules, or which we call monomers. You did a little bit of this, or you should have done it when you did protein structure and biology, and you had individual amino acids coming together to make a polymerization, and then you get a protein as the result. Here it's very similar, except they're not all amino acids. So here's ethylene. Polyethylene is plastic, or a type of plastic, I should say, HDPE. But so what we have here is there's a break of the double bond, which causes them to bond together, and you in this polyethylene molecule. This happens with lots of different things. So there's PVC, which is polyvinyl chloride. You also have styrofoam, which is polystyrene. But most of the plastics and things that you are aware of, they're all polymers. And you see them in other parts of your life. Now, this is a video we played in class. I'll put a link in the underneath this if you want to go watch it. It's a TED Talk that's pretty good about polymers. But some other places you might see polymers, or shrinky dinks is one. And I actually have some here. I don't know if I can take them off to show you, but I've got some shrinky dinks my lab mates made. Oh, I can't get it off. Oh, well, they're larger pieces of plastic, and you can draw on them, and they shrink down when you heat them up. Super balls are ones that they're resilient and they bounce really well. You've played with super balls before, I'm sure. And then silly putty, or slime and gack. If you've ever made gack or slime at in elementary school before, it's a polymer as well, or non-Newtonian fluid. And then nylon is another one. We actually do a little bit of this in AP chemistry at the end of the year for demos, but you can use sobosyl chloride and actually produce nylon and draw it out into a thread and use it if you wanted to, if that was possible. The last one I'm just kind of showing here is the making of slime, and this isn't showing you GAC, but polyvinyl alcohol is another polymer that can be polymerized further by adding it with sodium tetraborate or borax solution. Or borax is actually a detergent you can buy at the grocery store. And sodium tetraborate will actually increase the bonds between them, making a polymer of little plasticky like. With the PVA or polyvinyl alcohol, it makes a slimy substance like you see in the picture that guy's got on him. And you can make this with the colored glue, the blue glue that you see at Walmart or whatever, or grocery store. That blue Elmer's glue is going to be polyvinyl alcohol. Elmer's glue is going to be what you would use to make GAC, and you use the sodium borate solution as well for that. So that kind of concludes, or that does conclude this unit with you guys. This was the end of the year. It was kind of an interesting year, I guess I would say. Let's see if we can stop this share here. Oh, can I do that? I'm not sure I can. Yes, I can. So it's been a good year, interesting year, not quite what we had the last 2 years, but close. If you guys have questions, talk to your instructor, and perhaps we'll see you next year in AP Chemistry.